Welcome, judges, to this presentation. This is the presentation for Team Chronics, SIH Team ID 2723, problem statement title, SAR image colorization for comprehensive insights using deep learning. Problem statement ID, SIH 1733. The problem revolves around colorizing SAR images. Before we head into this problem, we must get a brief idea of what SAR technology is. Well, SAR stands for synthetic aperture radars, which is a technology that allows us to map out large geographical areas without the need of worrying about the weather conditions or the visibility. This is done by replacing conventional light with radio waves. The images are constructed by piecing together the reflections of these radio waves, much like how LiDAR or sonar technology works. SAR images have a huge impact on how we process or how we see the geographical landscape. They are rich in textural information and allow us to extract a huge amount of insights. But since visible light is not used, hence the images are always in grayscale. So we have to colorize them. This task of colorization is quite daunting, especially for traditional methods. There are also certain challenges that are faced during SAR image processing. Our idea revolves around creating a pipeline that is capable of taking in raw SAR images from the satellites and converting them into high resolution colored images. By tackling three major problems associated with SAR images: despeckling, colorization, and upscaling. We'll first look into despeckling. Well, SAR images are always littered with some amount of granular noise called speckle noise. This is generated due to the interference of out of sync waves. So, our aim in this part of the pipeline is to enhance the quality, smoothen out the noise, and prevent the major high level and low level textures and details of the image. Next up, we come to the colorization model, whose task is to predict or to color each pixel of the despeckled SAR image. Lastly, we come to the upscaling model, whose task is to increase the resolution or improve the quality of the colorized image so that it's easier for humans to extract information. We have laid out the entire pipeline structure in a flowchart of sorts, which is easily scannable by everyone and broken down into bite-sized information. Coming to the technical approach, as we said before, the model or the pipeline is divided into three models: the despeckling model, colorization model, and upscaling model. Tackling the despeckling model first, it is done by implementing a deep convolutional neural network that has 24 convolutional layers and 12 skip connections, which is borrowed from the ResNet architecture. This particular architecture was chosen because we had to preserve a lot of low level information like textures and minute geometries. Coming up to the colorization network, it implements a conditional GAN which has 8 convolutional layers and 3 skip connections. The model itself can be broken down into 3 smaller subtasks. First is generation of pseudo optical image from grayscale image. Next is feature extraction and edge detection using an improved Harris edge detection algorithm. And finally is the reconstruction of the image. Last model in our pipeline is the upscaling model, which implements a super resolution CNN with three convolutional layers for feature extraction, nonlinear mapping, and reconstruction. Here we can see a very detailed diagram of how the colorization model works. One of the major problems that we had when designing the algorithm was sourcing the data and processing it so that our model can learn well from it. We were fortunate enough to find data from the Sentinel 1 and 2 satellites launched by the European space agencies that allowed us to pair SAR images with optical images, greatly improving our model. Finally, we'd like to touch upon a bit about the loss functions that we have designed. For our despeckling model, we have used a combination of pseudo hover and TV loss, which allowed us to preserve the edges and also achieve a decent amount of smoothing. For the colorization network, we were using a combination of L1 loss and adversarial loss that allowed us to mitigate problems like vanishing gradients that is very common in deeper networks, and also to avoid the problem of grayish pixels which can be easily detected by the discriminator model. Finally, for the SRCNN structure, we were able to pick it up from a research paper that we have later cited. The entire pipeline, the entire three models have been designed and implemented using PyTorch, NumPy, OpenCV, and the entire pipeline has been designed to be served using a RESTful API developed in Fast API. The entire application will be containerized using Docker and deployed to AWS or Google Cloud. Coming on to the feasibility and viability, one of the major concerns that we have is the availability of computation power, and also the worry that this entire field is continuously being developed and ongoing research is happening. So we might need to reiterate on the models again and again. But if implemented correctly and in the way that we have thought, this could lead to improvement in decision making to a huge extent. Coming on to the challenges, as we have mentioned some before, the availability of datasets, preservation of low level information, and the accuracy factor of the models were one of some of the greatest challenges that we faced while developing the prototypes for the models. We tried to solve them by using deeper networks, implementing skip connections, developing hybrid loss functions, and using pre trained models to reduce the weight and the entire load on our systems. Coming on to the impacts and benefits, we would like to highlight our target audience, which includes government agencies, researchers, agriculturists, and many more people. Rather, anyone who is willing or who is wanting to extract some amount of information from geospatial data or geographical data. Our pipeline directly translates to faster, accurate, data driven decision making along with efficient resource utilization. To further look into the benefits, we can take in case specific benefits. For example, in agriculture sector, where detecting the crop health and irrigation patterns will be a great help. In the environmental sectors, monitoring of deforestation, climate change, this will be greatly benefited by our pipeline. And finally, military, which will directly lead to more accurate terrain mapping and real time intel gathering. Apart from that, it will also directly translate to faster disaster management and first responses. Before moving on, I would also like to address the cost or the economic feasibility of the entire project. Since the development is done by us. There is no charges associated with that. The major economic factor comes in when setting up servers and setting up GPUs or renting GPUs that will be able to train these models accurately and to the best of their limits. Apart from that, maintaining these models and improving upon them when new research comes out is one of the major economic factors of the entire project. Finally, we have referenced or we have cited three research papers that were of great inspiration to us. We have received these from IEEE and Nature magazine. Great, great thanks to all of these authors. With that, I would like to conclude our session or our presentation. Hope you like it, and thank you.